There's going to be a delay. There's we're gonna have to rotate some things. If you're not seeing things clearly, let us know what we need to fix. Yes, we want to start out with chapter 12. We're talking about this idea of correlation coefficients and how two variables are associated and trying to determine if two linear variables or two variables can be predicted using a linear model. So the first thing we want to look at is what is the correlation coefficient? Okay, so with our data, things don't work out perfectly all the time. Actually, they almost never do. And so we try to predict what's happening based on our best estimates of what we know. And so a correlation coefficient is basically telling us how tightly packed our data is around the line of best fit or the regression line. And so what we get is our correlation coefficients range anywhere from -1 to 1. Okay, and your R value always has to be between -1 and 1. So if my points were to line up perfectly in a straight line, then my scatter plot and my best fit line would look like this. Okay, so my data points are tightly packed. They're exactly on the line, actually. Okay, so this has a correlation coefficient of 1. That is the strongest positive linear correlation we can have. Okay, in this example right here, our data doesn't tend to be following any pattern at all. So the best fit line is going to average those points and run right through the middle. Okay, so these two variables aren't correlated, so our correlation coefficient is 0. Okay, so this would be something like if I'm saying, what's the relationship between your height and your test score? If those things don't have anything to do with each other, so we would expect a 0 correlation coefficient. Okay, and then if we have a correlation coefficient where our dots are perfectly lined up going downward, and our regression lines drawn on there, we'll go right through those points. And I drew them so I wouldn't miss it. We missed it. Okay, and this is an R equals -1, or that R value is -1. Okay, this means that our data is perfectly correlated in a downward, and the trend is downward. Okay, so your slope of your line, your regression line here would have to be negative, and here it would be positive, and here it would be 0. Okay, so correlation, it can be as strong as 1, strong as -1. These are equal in strength, just going in different directions. And the less correlation there is, the closer we get to 0. Okay, so if we were to draw one that has points that aren't in a straight line, but they're going somewhat downward, okay, then my regression or my best fit line is going to go through here somewhere. We know the slope's negative, but this might have a correlation coefficient of -0.8. Okay, so it's close to -1 because it's still pretty strong, but they're not exactly in line. Okay, so the closer to 1 or -1 you get, the stronger the correlation. The closer to 0, the less the correlation. Okay, any questions? Stop us if you need to.
Do you guys have questions?
All right, Mrs. Jones is going to take you through some calculator work for a minute.
All right, so before we get on the calculator, we're going to talk a little bit about what those different scatter plots and how they correspond to the correlation coefficient. All right, so if we take a look at this one, we've got kind of the data is not really bunched together, but you see that it has a positive, the line of best fit would have a positive slope. This one, same kind of thing, but it's more tightly held together. And this one would have more of a -1. This one might have a slight -1. This one kind of all over the place, but it's still kind of going in a positive direction. And then this last one is really all over the place. So our choices are -0.85, or sorry, yeah, 0.85 negative, and then -0.4, 0, 0.33, 0.87, and 0.99. So we're going to start with the 0.99. That's really, really close to 1, meaning that they almost all land right on the line of best fit or the regression line. So that's going to be this one right here. That has a 0.99 correlation coefficient because the data is really tightly packed around that line of best fit. And it's positive because it's going in the positive direction. Okay. Then we've got, well, let's do the one that's 0. Okay. This one is scattered all over the place. Okay, so this one, that just like what Mr. Shaw had up on the board, that you would just have that horizontal line because there really is no correlation with all of that. There's no line of best fit that really works. Okay. And then we've got a positive 0.87 and a negative 0.85. So let's do the negative point or positive 0.87. We have a positive slope. And if we said this one was 0.99, this one's going to be our 0.87. It's still packed around, but not as tightly as this option here. And then we've got our negative 0.87, or sorry, negative 0.85. That's going to be this one right here. It's going in a negative direction. And it's still pretty close, but not as tightly packed as like this one was. And then we've got this one starting to get a little more spread out, but it's still kind of going in that negative direction. So that's the negative 0.4. And then we have this one at 0.33. That's going to be this one right here because it's going up in a more positive direction, but the data is really spread out. Okay. All right. So now take out your calculators. We're going to stop talking about correlation coefficients and get into a problem from beginning to end. So we have a data set.
Is it data or data?
Data and data, both. All right, so if we take a look at this, this is a table. We have our X and our Y values. This table below gives the numbers of hours spent studying, and we're going to substitute the stats exam. So the hours of studying for the stats exam is our X value, and the final exam grade is the Y. So X is the independent variable, and Y is the dependent variable. So this is hours studied and final exam score. And we've added one more on here. The one hour of study that somebody got a score of 92 on there. So we have 277, 592, 170, 0, 63, 490, 275, 384, and we added on another one, 192.
For that kid that never has to study but does well.
Yeah, the kid that never has to study or studies just a tiny little bit but still does very well. So what you're going to do is on your calculator, we'll zoom in on this. You're going to go to your lists and enter those data points in. So my list 1 is the X values, hours studied, and list 2 is the final exam scores, the Y values. Okay. So we're going to do a scatter plot. So you're going to go to your second, hit your second, and then the Y equals. And we're going to do scatter plot. And this one is on, and we can choose. This is where we had done like the histogram and the box chart, the box and whisker charts. But this one we want it to be a stats plot. So we're going to do the scatter plot on that one. And then you hit graph. And I've already done this, but you'll have to hit zoom 9. And then this is showing you what our scatter plot is like. So that one that we added in, you can see it right up here. That's kind of our outlier. The guy who doesn't have to, or lady who doesn't have to study a lot, but gets a high score. Okay, so we tossed that one in so that we could go over this a little bit better. All right, so.
Okay, so if you guys made your scatter plot, we want you to make a prediction. What do you think the R value will be for that data? You guys can just put it in the chat box. What do you think your R value is going to be?
So type it in. You guys can see the scatter plot. What do you think the R value is? Type it in the chat box. High 80, low 90. Okay, so Ty says high 80, low 90. Wyatt saying 0.9.
He just copied Ty.
He did. Dawson saying 0.85. Eliza says 0.8. Kylie says 0.84.
One of them probably already written the test.
Yeah, somebody could have already run the test.
Actually, they don't. We have that.
Yeah. Okay, so all of your predictions, did you notice how all of your guys' predictions were all positive? Okay, that's because when we take a look at this scatter plot, a line of best fit would go up in that positive direction. Okay, so if you are making a prediction, you want to make it at least positive.
At least positive.
At least positive. All right, so you ready to switch the cameras?
Okay, let's switch for just a minute, then we'll switch back and do
Okay.
the test.
Let me switch it.
You're gonna have to rotate that as well.
Oh, that's right.
Comes up backwards. Yeah, so as we start the problem
Hold
now,
on. Not quite. There we are. Okay.
so we start our problem. We are doing a hypothesis test. That's kind of the main point of this in the end, is we have to set up our hypotheses before we can do anything. Okay, so if you've been following with Mrs. Jones, you've got your data in the calculator, that's going to be where we make all of our decisions. We have to set up our hypotheses first. So you see, if you've read the packet or watched the videos, this thing that looks like just kind of a cursive P, I don't even know how to write it. It's actually the Greek letter rho. Okay, so what we're saying here on our null hypothesis is that rho is equal to 0. Okay, rho is the population correlation coefficient. So R is giving us the sample correlation or coefficient. Rho is giving us the population. I'm looking at the camera, Mrs. Jones.
No, you're good.
Okay, so rho is the population correlation coefficient. Okay, so right here we're saying in our null hypothesis is that we're hypothesizing that the correlation coefficient is 0, which means they're not correlated at all. So then our alternative is going to say rho does not equal 0, which means there must be some sort of correlation. Okay, so we're using equal 0 and not equal 0 all the time. Okay, so we're gonna go back to the calculator now and actually run the test.
Hi guys.
And in between, you
get to see me. Right. Okay, so on our calculators, you just want to make sure, and when you do this on the test, you want to make sure that when you put your list in, that your list is accurate. Okay, so that your list, so you're not getting something wrong just because you typed something in wrong. Okay, all right, so we're going to go to the stats, come over to our tests. I like to go from the bottom up because the linear regression t-test, that's where we're going. Option F, linear regression t-test. And we want list 1 is our X and list 2 is our Y. So the X values were list 1, Y values are list 2. We don't have a list for frequency, and we are selecting the not equal to 0. So rho does not equal 0. And now we're going to calculate. So you'll notice up here at the very top, this is given in the form y equals a plus bx. Okay, so you're used to seeing lines written as y equals mx plus b or slope-intercept form, but this one, they're putting the y-intercept first and then the slope and the x second. So when you're looking at down here at the bottom, you've got a is equal to 69.8 and b is equal to 4.68. Those are the values up in here. So a is representing the y-intercept and b is representing the slope of our regression line, our line of best fit. Okay, so our test statistic, the t-value, is 2.534, and our p-value is 0.0444. Okay. All right. Oh, and you'll have to scroll down lower to see your r and your r squared value. So you have to keep scrolling down before you can see the r value. And let me see if I can zoom in a little bit more on that. Yeah, your r value here is 0.719. So for those of you who are estimating around 0.8, that's not too bad. Okay, so but this one, our correlation coefficient r is 0.719. Okay, switching
on that R value, you guys that are guessing 0.8, 0.9, it was actually like 0.99 before we added in the outlier. And that's why we added it in, so it didn't seem like we were trying to force you into studying for this exam, although that's what we're really trying to do here. There's definitely a positive correlation between your study time and how well you're going to do.
Mm-hmm.
Okay, so all that stuff that you got off the calculators here, our regression line, our R squared, our T, and our P value. Okay, so now we just need to interpret all of this junk. Okay, so there's two methods for determining what our decision is going to be. And so you guys keep seeing this t-stat or the p-stat, or sorry, the z or the t-stat. We haven't used it. This isn't the way we're going. Okay, so the methods are either using the p-value or using the critical value. We're using the p-value method. So just to clear up why you're seeing this all the time, we keep writing it, but we never use it. It's because we're using the other method. Okay, so what we got to do first of all, we're going to make a decision about our null hypothesis. Okay, so our decision is going to be based on our p-value. Okay, so remember we're talking about alpha as it relates to p. Okay, so in this case, we don't have an alpha. It wasn't given, so if it's not given, we use 0.05. So in this case, we have p is less than alpha. Okay, so what's our decision going to be if p is less than alpha?
All right, so type it into the text box. What's the decision? P is less than alpha.
And this applies same rules it's been since chapter 9.
Mm-hmm. Spencer is saying reject the null.
For Spencer.
What other people, what do you guys think? Because he had a question mark at the end. Dawson is saying fail to reject the null. Kyler, fail to reject. Ty is saying fail to reject. Eliza saying fail to reject.
Oh no.
I know. Jerica saying fail to reject.
All right, who hasn't answered yet? So Ty, you feeling a little outnumbered?
So Spencer saying he might be
Oh,
wrong.
Spencer's
Kylie is saying P is low, the null must go.
If P is low, the
P
null
is
must
low,
go.
the null must go. So you have to reject the null.
We're going to reject.
Okay, if P is low, the null has to go. You're rejecting the null.
Reject the null hypothesis here.
So,
Okay, so Spencer, never be afraid to stand alone. Ever.
yep, yes.
So we're going to reject the null. Remember, if P is low, the null must go. Okay. P is high, the null must fly. So in this case, our P is low, so we're going to reject the null hypothesis, which means that our evidence supports. We don't want to write this all out. Can I just say it? Okay, which
yeah, I think you
means
can
there's
say
sufficient evidence to support the null, or sorry, the alternative hypothesis, which means there is a statistical linear significance or association between our two variables. Okay, which means our linear model is appropriate. Okay, we can use this to make good predictions. Okay, does that make sense? Mr. John, you want to add to that?
Yeah, so when we're rejecting the null, we're rejecting the idea that that rho equals 0. We're rejecting that there is no correlation, which in turn leads us to say there's sufficient evidence to say, yeah, there is a correlation, and this line of best fit will make a good prediction line.
Good predictive model.
Yeah, a good predictive model.
That's what I meant to say too. Okay. Okay, so I need you to understand that because this kind of seems a little bit backwards when I think about it. Because we're saying we're testing the hypothesis of being no correlation, which means our evidence is supporting there is a correlation here. Okay, so we are saying that these two things are correlated. Okay, so that's going to be our decision. We're going to reject the null and say there's sufficient evidence to conclude that there is a correlation between the two variables. Okay, so now we need to interpret some other stuff, right?
Yeah, I'm going to pull up this in the packet. So if you guys in your packet, page 685. Let me switch this. Okay, so page 685 talks about this r squared, the coefficient of determination. Okay, this is a great spot if you're stuck on how to interpret what r squared really means. So page 685 in the packet, the coefficient of determination. All right, switch it back over. Just give me a second.
Okay, and lastly, we're going to interpret some of these stats we have up here. So let's start with the R value. Okay, so that 0.719, all it tells me is how tightly packed my data is around my line of best fit. Okay, so 0.79 is a general rule of thumb. If you're 0.7 or higher, you say it's a strong linear positive correlation. Okay, that's all that tells me. And the R squared, we're going to need you to memorize this line. Is that what you just showed them? Okay,
Yep.
that Mrs. Jones just showed you. So R squared is actually a percentage of the variability as it relates to these two variables here. Okay, so what we're going to do is we're going to say 51.7% of the variability in final exam score is due to variability in study time. Okay, so this line right here, if you just keep it the same, all you would change is your percentage, your Y variable, and your X variable. The rest of this line is going to stay the same. You're just going to change these three things. Okay, my open math talked about it a little differently. This is the way Snow is probably going to go, though. We're not going to talk about reducing variability at all. So 51.7% of the variability in the final exam score is due to the variability in study time, which means about 48.3% comes from other factors. Okay. Anything else we need to say on that?
Yeah, so would you write out just like the blank one that you do for Math 1? So this is your basic fill in the blank interpretation. Blank percent of the variability in the Y part, the
Y variable
Y variable, whatever the Y variable is representing, is due to the variability in the X, whatever the X variable is. And another way you can kind of think about it with the example that we were doing, so 51.7% of the variability or the change in the exam scores is due to the variability in study time. In other words, the study time is taking a little bit over 50% of that variability. It's due to just study time. Now, that other 48.3% is due to other factors. So what would those other factors be?
chat box.
Chat box. What would those other
other
factors
factors
be to cover that other 48.3%? That's the variability in the final exam score instead. So Spencer saying skill.
You know what you're doing. That's pretty good
It
indicator.
is. Practice. Dawson says practice. Are there anything else that could affect how well you perform on a test, on an exam? Your day, yeah.
Attitude.
Yeah, your attitude. Could even be like anxiety. Okay. All right. So that would account for those different factors that this isn't working with are the other 48.3% of the variability in the scores. All right. Now let's go to predicting. So now that we have this line of best fit, I'll move this camera over here. All right.
We on?
Okay. Yep, we're good.
All right, so now we're going to talk just a bit about these variables. We want to interpret the slope, the y-intercept, and make a prediction. Okay, so on this one, remember this is written in kind of backwards form. So we have b plus ax. Okay, so this part in front of the x, this is our slope. Okay, so all of your open math questions ask you to interpret that slope in context of the problem. Okay, so our slope describes, remember, you guys remember slope, you've been doing it for years, is change in y over change in x. Okay, so our y variable was test score, and our x variable was time spent studying. So a 4.68 slope means for every 1 hour you study, your test score, let this take forever to write, increases by getting ahead of myself, 4.68 points.
And in your interpretations, you want to be specific. You want to make sure you have the units that you need to when you're describing it. So for every 1 hour you study, your test score increases by 4.68 points.
Okay, does that make sense? Okay, so remember your y variable is changing. This is like 4.68 over 1, which is no number down there. So every change in x, there's this change in y. Okay, so then our y-intercept, this number right here. Okay, remember the y-intercept happens when x is 0, so we're saying if you don't study, we predict a score of 69.8. Okay, so the y-intercept is when x is 0. So someone that does not study, we would predict a score of 69.8. Okay, and lastly, the whole purpose of making this regression line is to use it to make predictions. We want to predict, if you spent 7 hours studying, what would your score be? I have to put on here, what is your predicted score? I guess that's a question.
Mm-hmm.
Okay, so how do we go about figuring out or making that prediction?
What would we do with that 7? Type it in, yeah, type it in the text box. Kyler says plug it in. Plug it in where?
Plug it in. It's obvious, right?
In the X. Yep, substitute that in the X.
So this is our hour spent studying, which has been our X variable all the way through. So to make that prediction, we're going to say 69.8 plus 4.68 times 7. So I'm going to wait for Mrs. Jones to calculate for me.
Oh, I forgot a parenthesis. Of course.
A little over 100, about 105.
Yep. 102.56.
Okay, so we predict a score of 102.56. Okay, so I purposely made this one go over 100. I don't know if it's percentages or not, or what the total is. But that would be our prediction. So if this only has 100 points possible, or 100% possible, our prediction's telling us we're going to get a score that's better than possible. So I chose that one because I knew it happened. Remember, these are regression lines. They're models. They're not perfect. They're just our best guess based on the data we have. So this is an observation or a prediction based on what we've observed. So it doesn't have to be exactly accurate. It's just saying, yeah, you'll do better based on what we see. Okay, so obviously if there's a maximum score, this may or may not make sense in the context, but that is what we're predicting based on the data we have available. All right, so any questions about interpretation?
Nobody's speaking up.
All right, this will mean our 3-camera system is a good way to teach a lesson.
Did is this 3-camera system working? We got some yeses. Okay.
We got a power menu, right?
Okay, so I'm gonna stop recording.